because yesterday there were disturbances, and I'm very sorry for that. Hopefully, from now on, with the better internet connection, this will not be there. So let's start with the lipids. Lipids are among the macronutrients that we say are required for the human body. So, lipids, if we look at it, among the macronutrients, this is a diverse group of hydrophobic molecules. Okay, among the macronutrients, it is the only one which does not form polymers. If you look at carbohydrates, although you have the sugars, they can form polymers such as starch and glycogen. Proteins form polymers of amino acids. However, lipids do not form polymers, but they are large biological molecules. On the other, the second unique point of lipids is that they have no or little affinity for water. So this all lipids therefore are hydrophobic in nature, and they mainly consist of long hydrocarbon chains which form nonpolar covalent bonds. The most important biological lipids are the fats, the phospholipids, and the steroids. They all come under the large class as lipids. So if you look at the classification of lipids, a very simple classification of lipids, we have the simple lipids, we have the complex lipids, we have precursor and derived lipids, and the miscellaneous lipids. Among the simple lipids come the fats and oils that all of you consume, plus also the triglycerides which are present in the human body. And these triglycerides are esters of glycerol. We also have waxes, which are long chain fatty acid esters of monohydroxy alcohols, as we will see later. Then you have the complex lipids, which you find, which are the phospholipids. They are complex because they contain a phosphoric acid group in them. You have the glycolipids, which are lipids joined to sugar molecules. Then you have other complex lipids, such as those which have got sulfur, the sulfolipids, those who have got amino groups, the aminolipids. And then, of course, you have the derived lipids and the fat soluble vitamins, and the vitamins we will be discussing tomorrow. Lipids basically are in chemistry are classified into the hydrolyzable lipids and the non-hydrolyzable lipids. Under the hydrolyzable lipids, the word hydrolyzable means that these are all esters and they can be hydrolyzed either chemically or enzymatically into their basic constituents. So you have the waxes because they are esters, the triglycerides which are esters, and so also the phospholipids which are esters. On the other hand, the non-hydrolyzable lipids, you have the steroids such as cholesterol, testosterone, aldosterone, vitamin D3, vitamin D2, the fat-soluble vitamins, that is the vitamin D2 and D3, and then you have the eicosanoids. They are called non-hydrolyzable because they cannot be broken down by in the presence of water. Then what are the physiological functions? Lipids have two functions. One is the physiological function and the other is their role as dietary fat and oils. So if you look at the fatty acids in the human body are components of several classes of lipids, and they are used mainly as metabolic fuel. When we do nutrition, we will see that you can break down the fatty acids into acetyl-CoA, and acetyl-CoA will then go into the Krebs cycle and it can form ATP, which is the fuel for the body. Triglycerides also are the storage forms of the fatty acids in the body. They are storage form of the fatty acids in the body, and they will be broken down into glycerol, and the fatty acids again serve as metabolic fuel. And you have the phospholipids, which are very important lipids, components of the membrane, and which are responsible for signal transduction. The sphingolipids, these are components of the membrane and again very important for signal transduction. Cholesterol, the steroid, is a component of membranes, and also it serves as a precursor of bile salts and steroid hormones. Bile salts, which are made with the cholesterol backbone, help in lipid digestion by emulsifying the fats that you take through your diet. Steroid hormones, again, they basically come from cholesterol, and they are give intracellular signals that regulate gene expression. The eicosanoids, prostaglandin, thromboxanes, leukotrienes, these are important regulators of the immune function of the body. And then you have the vitamins, fat-soluble vitamins A, D, and K, as we will see in another webinar, their importance and their physiological role. So, what is the function of the dietary fats and oils? One, they are concentrated sources of energy. You will see that for a single gram of fat that you take through your diet, it produces 9 kilocalories of energy. Whereas if you take the same 1 gram of carbohydrate or 1 gram of protein, you will see that it gives you only 4 kilocalories of energy. The fat that we take also are carriers of the fat-soluble vitamins. The third point is the dietary fats, and one of the most important is that they are the sources of the essential fatty acids. What we mean by essential fatty acids is that these fatty acids cannot be synthesized by the body, and so therefore have to be taken through the diet. Fats also are responsible for organoleptic properties. So it is important for your food to taste good. So one of the properties of the fat that you take, the dietary fat, is that it imparts taste and flavor to the foods. And I'm sure most of you know what the flavor is when there is fat and when there is no fat. And also fat add to the satiety value. So I'm sure when most of you have eaten, a large amount of sweet with plenty of ghee in it, you will feel full. That is, you'll be satiated. So fats actually contribute to what is known as the satiety value. Now let's look at the simple fats. The simple fats are the triglycerides, or what we call as the fats and oils that we consume. These fats are constructed basically of only two types of molecules. One is the backbone. This backbone is glycerol, which is a trihydroxy alcohol. That means it's got 3 hydroxyl groups, and each one of these hydroxyl groups is esterified, is in an ester bond with a very long chain fatty acid. So this makes up what is known as the triglycerol, also known as triglycerides, also known as triacyl glycerols, and many a time will be abbreviated as TGs or TAG. So basically you remember that it has a backbone of the glycerol and in ester with fatty acids, and these fatty acids can vary. So because you have 3 different fatty acids or 3 similar fatty acids, and there are 20 different types of fatty acids, there is no single formula, a molecular formula, which can describe a triglyceride. Unlike in carbohydrates, you see the sugars, we always say it is CnH2nOn. So it is like C6H12O6. The triglycerides, just to recap, a glycerol backbone, and you have the three fatty acids. Now, in the triglycerides, it is the most common lipid in both foods and the body. It makes up about 95% of lipids found in foods. And when added to food, it's add texture, it makes the meat tender, it preserves freshness, and in the human body, the triglycerides are stored in the adipose tissue for energy. So let's look at a triglyceride. Here is a very simple triglyceride where all the three fatty acid molecules are stearic acid, and so therefore it is called a simple triglyceride. On the other hand, you have another triglyceride where on every carbon you have a different fatty acid. So here what you have is a mixed triglyceride. There is no hard and fast rule on which fatty acid should be placed where. Whether all the three should be different, whether all the three fatty acids should be the same, whether two should be the same and one should be different. There is no hard and fast rule. If the triglyceride is a solid at room temperature, then it is called a fat, whereas if it is a liquid at room temperature, it is known as an oil. And we will see later why they are solids and why they are liquids. Generally, the triglycerides which are obtained from animal sources are solids, whereas the triglycerides that are obtained from plant sources are oils. So we generally speak of animal fat and plant oils. So let's come to the fatty acids. If you look at the backbone, it is only glycerol, and so glycerol cannot change. But however, the fatty acids, which form the side chain of triglycerides, you can have 20 different fatty acids which have varying length, which have varying saturation, that means the number of double bonds, and also of varying shape because of the geometric isomerism. So these are the building blocks of triglycerides as well as phospholipids. And fatty acids that you find in triglycerides are all even chain. You do not find odd chain fatty acids in triglycerides. So they can range anywhere from 2 carbon to 26 carbon, and all these fatty acids are monocarboxylic fatty acids. So that means at one end of the molecule, they have got a carboxyl group, and that is called the alpha end of it. And at the other end, they have a methyl group, and that is known as the omega end. So remember the alpha end and the omega end, because when we write fatty acids or we name fatty acids, we name them either from the alpha end or from the omega end. So fatty acids vary in length. They are short chain if they range from about 2 to 4, and these are all liquids at room temperature. Medium chain fatty acids have a carbon number of 6 to 10. The long chain fatty acids have about 12 to 20, and these are the most common fatty acids that are found in the foods, and they are all solid at room temperature, especially stearic acid, which is C18, palmitic acid, which is C16. The very long chain fatty acids are C22 and above. Now, fatty acids vary in saturation acid. All the carbons on the fatty acid are bound to hydrogen, and you know that in organic chemistry, when you want to balance the equation or balance the bonds in the carbon, there are 4 bonds. So you have, if you have methane, CH4, you see one carbon is attached to 4 hydrogen. All the fatty acids which are saturated, that means where there are all the carbon have got single bonds attached to them on all sides, These fatty acids are solid at room temperature. They generally have a higher melting point, and fats which are made up of high levels of saturated fatty acids are known as saturated fats. And because they have saturated fatty acids, these fats are solid at room temperature. A very good example is animal fats which are saturated. So you see butter, which is a solid at room temperature. Then the most commonly occurring fatty acids in the triglycerides are myristic acid, palmitic acid, and stearic acid. Although the occurrence of the fatty acids depends on the oil. So you will see in some cases like coconut oil, you have lauric acid and myristic acid. In palm oil, you will have more of palmitic acid. Now, these fatty acids are carboxylic acids. And from your organic chemistry knowledge, you should remember that all carboxylic acids are weak acids. So, what is an acid? An acid is something which can donate a proton. So this is a weak acid, and being a weak acid, it can protonate, and you can have the carboxylate, negative carboxylate ion, and you can have the proton. The pKa value is about 4.8. So this is the structure of, to show you, this is the structure of palmitate. So this is a saturated bond. So it is a saturated fatty acid. All the carbon are linked through only single bonds, not a double bond. And so therefore this is known as a saturated fatty acid. Coming to the unsaturated fatty acid, the fatty acid will contain maybe a double bond, one or more double bonds over there. So if it contains one double bond, it is known as a mono unsaturated fatty acid. And the best example is oleic acid, which is made up of 18 carbon, and it has a single double bond, and oleic acid is present in high concentrations in olive oil. Then you have the polyunsaturated fatty acids, which have two or more double bonds in the carbon skeleton. And the examples are, you have linoleic acid, which is again 18 carbon, and it has two double bonds. You have alpha linolenic acid, which is 18 carbon, has got three double bonds. And you have arachidonic acid, which is a 20 carbon fatty acid with four double bonds in it. Because they have these double bonds, or these double bonds are unsaturated, most of the oils containing high levels of the polyunsaturated fatty acids or PUFA will be liquids at room temperature. They have a lower melting point, so all these oils which have got high polyunsaturated fatty acids have lower melting point, and these uh, or fats containing PUFA will be liquids at room temperature. The best example are the plant oils and the fish oils. I'm sure most of you know about the plant oils that you use at home, either sunflower oil, safflower oil, rice bran oil, groundnut oil, sesame oil. All these are oils, they are liquids at room temperature. And if you look at their composition, they will have a large amount of unsaturated fatty acids. So a saturated fat will have a large amount of saturated fatty acids, and so therefore will be a solid at room temperature. The unsaturated fats have got unsaturated fatty acids in their backbone, and so therefore they are liquids at room temperature. Now, just to tell you about the saturation and the unsaturation and how it affects the food fats, you look at the fats that we take commonly as vegetable oils or the dairy products or the animal fat that is taken. You will see that they are not made up of a single triglyceride. It is made up of a mixture of simple and mixed triglycerides. They will contain a variety of fatty acids which differ in chain length and in the degree of saturation. The melting point of these fats and oils will depend on the fatty acid composition. So now look at this figure on the right hand side and you look at olive oil. When you look at olive oil, what you see in green here is the unsaturated fatty acid content, that is the C16 and C18. So you can see a large amount of the oil contains unsaturated fatty acid, and this accounts for it being a liquid at room temperature. The higher proportion of these fatty acids, as I said, it increases the melting point. Now let's look at butter. Butter has got a large amount of that is the saturated fatty acids, but it also has got unsaturated fatty acids, and it has the lower carbon number saturated fatty acids. So if you look at the saturated fatty acid content, it makes it a solid, but because it contains some unsaturated fatty acids in it, you will see that it is a soft solid at room temperature. Many a times, we keep the butter in the refrigerator because at room temperature, you see, it will be soft and it will become soggy. So we keep it in the fridge so that it is hard. But look at the animal fats, such as beef fat, or you look at pork fat, which is large, you look at their structure. The major portion of the beef fat is the C16 and the C18 saturated. And because it has more than 50% of C16 and C18, beef fat is a hard solid. And so even at room temperature, it will remain as a hard solid, and there is no necessity to keep it in the refrigerator. And also you have to remember that a fat will depend on the external temperature. So we say that oils are liquids at room temperature. But many a time when you go to a cold place, for example, if you take coconut oil and you go to a hill station or you have gone to Srinagar, you will find that it solidifies because the melting temperature of coconut oil is higher, and so in these cold places you have the coconut oil can solidify. So this is just to show you that in a fat, because of the saturated fatty acids in it, the triglyceride molecules will be very close to each other and compact, and so it will be hard and it gives it the shape. Whereas the unsaturated fatty acids, because of the difference in the fatty acids, they can have bends, and they will be dispersed in it, making it a liquid. So saturated and unsaturated fatty acids also help to give the shape to foods. Now let's come to the how to differentiate between the fatty acids. Now earlier we have been only discussing about the numbers, that is, we say the small chain fatty acids, the medium chain fatty acids, and the long chain fatty acids, and we talked about saturation and unsaturation. Now let's look at how we name them based on their double bond location. So generally fatty acids are named based on the first double bond location. So you must have commonly heard of people speaking and nutritionists always talking about omega 3 and omega 6. So what is this omega 3? So the first double bond is at position 3 from the omega end. Recollect, the methyl group is the omega end and the carboxyl group is the alpha end. So an omega 3 fatty acid is the third carbon from the omega end. So 1, 2, and 3. So you have omega 3. You can have another double bond here or here, but the naming will go from the omega end. So this is alpha linolenic acid, and here you have the carboxyl end. Now coming to an omega-6 fatty acid, the name itself suggests that the first double bond is at the sixth carbon. So you have 1, 2, 3, 4, 5 and 6. So the first double bond is there, and that is linoleic acid, which is an essential fatty acid. Now the same acids can be named differently if we count from the carboxyl end or from the alpha end. Now, fatty acids vary in shape also, not only because of the size, but also depending on the double bond, that is the configuration of the double bond. And you know, a double bond configuration, it can be cis when all the uh, additive thing, or the molecules which are there, or the atoms, are on the same side of the double bond. When they are on the opposite side of the double bond, it is known as a trans form of is the trans double bond. So you have a cis double bond and you have a trans double bond. So if you look at oleic acid, recollect oleic acid is C18 with a single double bond. It is 18 is to 1. So in the 18 is to 1, if you look at the double bond, the hydrogen atoms attached to the carbon are on the same side of the double bond. The same C18 with a single double bond, if the hydrogen are on opposite sides of the double bond, it is ylidic acid. And this is known as a trans fat. So any fat containing these trans fatty acids will be known as containing trans fatty acids or as trans fats. So here you have the cis form, and then you also have the trans form. And the melting point of fatty acids with the cis form is much lower than a similar fatty acid with the trans form. And you will see this in this slide, where it shows you have three fatty acids all having carbon 18. So you have stearic acid, which is a saturated fatty acid without a single double bond, and you see the melting point is 69. You have ylidic acid, which is an 18-1, which has a trans double bond at the ninth position, and the melting point is 44. Whereas oleic acid, which has the cis double bond, the melting point is 3. So trans fats have a higher melting point than the cis fats. What is to be remembered here is the trans fatty acids are not good for health, because unlike the cis isomer, these trans fatty acids tend to increase the total and total cholesterol as well as the LDL. So they increase the LDL concentration and they decrease the HDL concentration. So because of this, concerns are there, and regulators and nutritionists have decided that there should be a regulation to the dietary intake, and FSSAI has in most of the foods laid down the standards for trans fatty acids, which it says should not exceed 5%. It will be brought down to 2%, and in a few years it has to be absolutely absent. So you need to look at the regulation. A recent notification has come on trans fatty acids. Now coming to the nomenclature, actual nomenclature in terms of organic or chemistry or IUPAC, they all have got common names and they have got systematic names. If you look at the saturated fatty acids, it will end with NO8, and you see palmitic acid, is, the common name is palmitic acid, whereas the systematic name is hexadecanoate. So 16 and saturated. In unsaturated fatty acids, you see it is enoate. So you have palmitoate, which is again unsaturated hexadecyenoate. So where enoate means that it is unsaturated. Just like you have alkane, which is saturated, and you have alkenes, which are unsaturated. So this table just lists out the common fatty acids in increasing carbon number. It shows you the common name as well as the systematic name and what the structural formula is. So the position of the double bond, as I said, in addition to it being named from the methyl end, so you have omega-3 and omega-6. You can also said it can be named from the alpha carboxyl end, and that naming system is known as the delta system. But generally in food science and food analysis, we only talk about the omega-3, the omega-6, we talk about unsaturated, and we talk about saturated. The delta system is uncommon, but as chemistry students, you should know this nomenclature system. So if you have palmitoleate, that is the 16 carbon fatty acid, it says it's got a single double bond, and the double bond is from the ninth carbon from, it is from the ninth carbon from the alpha carboxyl end. So if this is the alpha carboxyl end, you have 1, 2, 3. You have 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is delta 9. So the carbon double bond is between 9 and 10. And then the other system I already explained to you is you have the omega. So if we have to name palmitolate from the omega end, if this is the omega end, the same double bond, which was delta 9, becomes 1, 2, 3, 4, 5, 6, 7. So it becomes 7, 8. So it becomes delta 9 or omega 7. So this is just to show you some of the fatty acids, the long chain fatty acids. So you have stearic acid is a spelling mistake, also known as octadecanoic acid, palmitic acid, which is known as hexadecanoic acid. Then you have oleic acid, which is known as cis-9 octadecanoic acid. And you have linoleic acid, which is known as 9,12 octadecadenoic acid. That means there is 18 carbon. So then you have what is known as the essential fatty acids. The essential fatty acids are fatty acids that are not synthesized by the body, and they need to be taken from the diet. So you look at linoleic acid, what I have put over here is to know all the different types of nomenclature. So 18,2 delta 9,12 is the same as 18,2 omega 6. Alpha linoleic acid is 18,3 delta 9, 12, 15, or it is 18,3 omega 3. These fatty acids, if not taken in sufficient quantities, can result in a deficiency. And in infants, if the essential fatty acids is not there, they develop scaly dermatitis and growth retardation. And this is also seen in cystic fibrosis. The role of the essential fatty acids is these two are precursors for the eicosapentaenoic acid and the docosa hydroic acid, that is the DHA, which is involved in brain function. So it's very important, EPA and DHA, for growing children and for infants. And that is why you will find that most of the advertisements, if you are looking, you see Horlicks or you see Complan, or you see any of the food, it says, enriched with EPA or enriched with the docosa hexanoic acid, the DHA. That is just to say that it is good for the brain. They are also precursors of prostaglandins, thromboxanes, and leukotrienes, which are required for regulating the immune system, for blood clotting, for inflammatory as anti-inflammatory agents, and for regulating blood pressure. Other important PUFAs are the arachidonic acid, which is 20 with 4 double bonds, and it's omega-6. Okay, it is a common precursor of icosanoids. The icosanoid pentanoic acid is this, and this is the structure for docosa hexanoic acid, where 22 and you have 6 double bonds, and it is an omega-3 fatty acid which is present in fish oils. Because these essential fatty acids are present in fish oils, fish oil tablets or capsules are also being promoted as nutraceuticals and in functional foods. And you will see examples when we have the webinar on nutraceuticals. So the reason is the omega-3 fatty acids are very important components for the developing brain and for the retina. So food sources of omega-3 fatty acids, you see most of the food sources are the fish, and you have very little among the beans, very little omega-3 and 6, and this mainly comes in soybean. So therefore, for vegetarians, it is very important to substantiate the diet with omega-3 and omega-6 fatty acids. Now we have another important group of fatty acids which have health promoting effects, and that is the conjugated linoleic acid. So conjugated linoleic acid is a polyunsaturated fatty acid, and this is a unique fatty acid in that it contains both the cis and the trans double bond in a single molecule. So you have linoleic acid, you see it is 18,2 and it is N6, but you see it has, the linoleic acid has got this bond, which is the, now if you look at the conjugated linoleic acid, you see that in the conjugated linoleic acid, as I said, you will have both the cis as well as the trans double bonds. So you have CLA, one which has the cis double bond at 9 and the trans double bond at 11. And then you have conjugated linoleic acid with the trans double bond at 10 and the cis double bond at 12. Now, excuse me, I said linoleic acid was a conjugated acid. It is not linoleic acid which is a conjugate. It is conjugated linoleic acid. There are two forms of linoleic acid which are conjugates, and these are very important and required for health. They also come under the nutraceuticals. So they are being promoted as nutraceuticals or as functional foods. So here is a list of animal sources of plants and oils. And if you look at the thing, you see we have almond oil, you can have blackcurrant oil, you can have jojoba oil, linseed oil, and now each one of these oils is being promoted for its nutraceutical or bioactive, because there is some bioactive principle in each one of them. Among the animal oils, you see we have hard butter, you have lard, You have the whale oil, which is also now a nutraceutical. And then on this side, what you see is a typical fatty acid composition of the oils, commonly used oils, and you see mainly they contain, the 16, 18 carbon and the unsaturated fatty acids. So this is just typical. It has to be, there are several other oils, and each oil has got a golden signature. And with the signature of the fatty acid, it is easy to identify one oil from the other. So just look at olive oil. You see olive oil has got 71% of oleic acid. Similar to that, you have low erucic acid, which also, or rapeseed oil, which has got 62% of oleic acid. Now, let's look at, you have seen the nomenclature, you have seen the sources of all these oils. So now just let us look at some of the properties of triglycerides. The triglycerides, because they are esters, are easily hydrolyzable. They can be split into their constituents of glycerol and the fatty acid, either by a strong acid or by an enzyme known as lipase. So either by acid hydrolysis or by hydrolysis in the presence of the enzyme lipase, you get glycerol and 3 moles of the fatty acid. And hydrolysis of triglycerides of the in fats and oils is responsible for rancidity, because free fatty acids are produced. The free fatty acids are prone to oxidative degradation, and it results in the rancidity of oils. Then oils can also be hydrogenated. That is, oils which are liquid at room temperature can be made solids by saturating the unsaturated double bonds. And this saturation of the double bonds, or the hydrogenation of oils, is done in the presence of hydrogen over a catalyst nickel. And once it is hydrogenated, the melting point increases. I'm sure all of you know about vanaspati, or what is known as dalda, which is a hydrogenated vegetable oil. The vegetable oils used in the hydrogenation vary from company to company. So here is the example of a vegetable oil. Say you have glyceryl trioleate, you have the unsaturated fatty acids attached, and if you pass hydrogen in the presence of nickel, you will see that it gets hydrogenated, and you have glyceryl tristearate, or you get the solidified form. So margarine, soft margarine, all the fats that are used in the bakery industry are all hydrogenated fats. So if you look at your analysis of fats and oils, you will see that in the hydrogenated fats, we have a parameter for nickel, which says the level of nickel should not exceed X. So why is this? That is because nickel is used as the catalyst, and some amount of nickel may have got into the hydrogenated fat, and so therefore FSSAI has set a limit for nickel in hydrogenated oils. Then the triglycerides are can be hydrolyzed in the presence of alkali. See, they are hydrolyzed in the presence of acid to give you the glycerol and fatty acids. In the presence of alkali, they can be hydrolyzed, and the fatty acids which are liberated get saponified. So what we mean by saponification is In the presence, because the alkali is sodium hydroxide, you get a sodium salt form, and that sodium salt of the fatty acid is known as soap. So you have the triglyceride in the presence of sodium hydroxide, also known as lye, Lye, in the presence of heat, can break it down into glycerol, and these three fatty acids released will form the sodium salt of the soap. If you use potassium hydroxide, you will get the potassium salt. And generally, in the softer soaps and the liquid soaps, they are made by saponification of oils that contain polyunsaturated fatty acids. So, in many of the advertisements on soaps, you will see made from pure coconut oil or made from some plant oil. But most of the soaps are made from animal fat, that is lard and tallow, and a few are made from coconut oil and palm oil. All the soaps, the way they work is they work in the same way, but they have different properties based on the fatty acid composition of the base oil that it is used. And that depends on the length and the degree of unsaturation. As I said, if you have a soap which is soft, that means it is made from an oil which contains a large amount of unsaturated fatty acids. So now let us see how the soaps work. The soaps work basically similar to emulsifiers that we use in the food industry. So, what is an emulsifier? An emulsifier is something which actually allows water and oil to mix. So, an emulsifier must be double headed. If it has to allow oil and water to mix, you know oil is hydrophobic, you know water is hydrophilic. So therefore, this intermediate must have both the hydrophobic part and the hydrophilic part. And that is what a soap has. So if you look at a soap, it has a long hydrophobic tail because of the fatty acid, and it's got a polar head because of the carboxylic acid, and that is attached to sodium. So if you go back and you see all the soaps are sodium salts of the fatty acid. So this is the polar end and this is the non-polar end, and that is what an emulsifier is. So soap is an emulsifier, and then in the preparation of soap, you can add pumice stone or sand to make it rough. You can add perfumes and essential oils to give it the aroma. You can add dyes to give it a color, and you can have fragrant soaps. You can also have bubbles in soaps by blowing air into the molten soap. Okay, and then you have soaps which are liquid soaps like your hand wash soaps, your shampoos which you use for your hair, and also the shaving creams. But a soap is a soap, whether it is a liquid soap or it is a hard soap. It has to remove the dirt or the grime which is either on your hands or on your bodies. So how does soap do this? So how does soap work? So you have a lot of dirt and grime usually stuck to the skin or the clothing, and this comes from your body oils or the cooking fats, etc. Now these are immiscible with water. That is, all oils are immiscible with water. Now when you add soap to any dirt which contains this grime, the hydrocarbon tails, that is the long tails of the soap, they dissolve the oil and the dirt, and the ionic heads, that is the carboxyl heads, they remain in the aqueous phase. All the hydrophobic tails go in, and they take the dirt along with them in, and the water will now be attracted to the sodium which is outside, and it will get washed away. So no longer will the oil or the glue dirt be glued to your clothes also. So basically, soaps act as emulsifiers. Now, fatty acids and rancidity. As I said, fats are easily hydrolyzable because the ester bond can be broken. You know, fats contain unsaturated double bonds, that is, unsaturated double bonds. So these are prone to oxidative degradation. So a fat can be broken down by hydrolysis, as well as a fat can get spoiled through oxidation. And if you look at the oxidation, fats containing more PUFA are highly prone to oxidation compared to MUFA and to those containing saturated fatty acids. So rancidity is a major concern of the food industry, and you will see that you cannot keep oils for a very long time, more than the use by or the shelf stable date, because they tend to undergo either oxidative degradation, that is oxidative rancidity, or hydrolytic rancidity. And when an oil becomes rancid, what you get is an unpleasant odor. So where does that unpleasant odor come from? The unpleasant odor comes from the oxidation of the unsaturated fatty acids to smelly compounds such as malonaldehyde. Generally, you can prevent rancidity by adding antioxidants or by limiting the exposure to oxygen, heat, and light. If you look at olive oil, you see most of your olive oil bottles will come in dark green or dark amber color bottles, preventing it from light, because you know olive oil contains a high level of oleic acid, about 72% of oleic acid, and can easily get oxidized and rancid. Now let's come to the next group of fats, that is the phospholipids. The phospholipids, also like the triacyl glycerols, are esters, but there are two types of phospholipids. One is which has a glycerol backbone, and the other is which has a sphingosine backbone. The phospholipid, which has a glycerol backbone, has two fatty acids in ester at SN1 and SN2 position, and in the SN3 position, it's esterified by phosphoric acid, which is further esterified by an alcohol. Whereas in the sphingosine, you have a single fatty acid, and you have at the third position, you have phosphate and alcohol. You see that this is sphingosine, it differs from glycerol. So phospholipids, they have got two fatty acids, a phosphate group attached to the glycerol, and the phosphate group can be esterified by either choline, serine, or ethanolamine. So if it has got choline, it is known as phosphatidyl choline, or this is lecithin. If you have serine, it is phosphatidyl serine. If you have ethanolamine, it is phosphatidyl ethanolamine or cephalin. So phosphatidyl choline, you find plenty of phosphatidyl choline, especially in egg yolk. And you see egg yolk, the lecithin in that acts as an emulsifier. So lecithins are used as emulsifying agent, and you see they are used in a large number of foods, especially in the bakery and in the confectionery industry. Once again, phospholipids, just like a soap, are double-headed. So they have both a hydrophobic end as well as a hydrophilic end. The fatty acid chains contribute to the hydrophobic part of it, and the phosphoric acid and the ethanol or thing contribute to the hydrophilic. So the importance in physiology is that the phospholipids play a major role in what is known as the lipid bilayer, that is the phospholipid bilayer there. And phospholipids, just like soaps, are used as emulsifiers, but these are used as emulsifiers in food. So this is the structure of the phospholipid. So you see phosphatidylserine. So it has got the glycerol backbone. It's got two fatty acids which give it the hydrophobic property, and then it has got the serine group over here, or the ethanol amine, which gives it the polar end of it. So if you represent a phospholipid, you have a polar head and you have a non-polar tail, and so therefore they are used as emulsifying agents, and we will see how they help or they form what is called as the phospholipid bilayer in membranes. So when the phospholipids are added to water, you will see that they arrange so that all the polar heads face the water and all the non-polar heads face each other, forming what is called two layers. So that is why this is known as the bilayer arrangement in cell membranes. So here you have one layer of phospholipids, and here you have another layer of phospholipids, forming the bilayer in the membrane, which is very important for physiological activities. Now let's come to some of the properties of fats and different types of fats which are there in foods. So lipids, if you take water and you add oil, you will see oil will float and water will be at the plate. So to make the lipid go into solution, you have to use emulsifier. So what does an emulsifier do? The emulsifier tends to make the fat and the water mix, and it forms what is known as a globule. So look at mayonnaise. Mayonnaise is an it is an emulsifying of egg white, and then you have a fat, oil, some oil, and you have moisture. But because of the emulsifier added to it, it could be a phospholipid or it could be a lecithin, and then shaken up, it breaks down the globules of fat into smaller droplets and makes them go into solution. So a very good example of an emulsified solution or a suspension which is there is milk. So in milk, you see you have got fat, and it is emulsified. The protein in the milk helps to keep the fat in solution. Now, if you shake the milk for a very long time, you will see that it will separate into that. Similarly, if in digestion, when you take lipids or fat through the oral route, they have to be broken down into fatty acids to be taken up by the body. But if you see, the whole digestive system is hydrophilic. So how does the lipid break down in a hydrophilic milieu? So there is when the bile comes in, and the bile emulsifies the fat. That means it breaks down the fat into very small globules, which then can be easily acted upon by the lipase, which is produced by the pancreas. So let's come to the sphingomyelin. They do not contain a glycerol backbone. They have a sphingosine backbone. And if you look at the sphingosine backbone, this is the structure of the sphingosine backbone. So you see you have a fatty acid, a phosphate, and an alcohol. And these sphingosines are very important in the brain and in the nerve cell because they line what is known as the myelin sheath. And so the nerve cells, they play a major role in the nerve cells. Then you have the cerebrosides, which are simple neutral glycosphingolipids. They are made up of sugar and lipid. So the cerebrosides are made up of galactose, and they have the hydrophobic tail, which could be a fatty acid. And the cerebrosides are also known as glycosphingolipids because here you have sphingosine and here you have a sugar on this. And these are predominantly, you see the name itself, cerebroside, suggests that it is in the cerebrum or in the brain. And so you find them mainly in the brain. Sterols, all of you know about sterols. They are more complex than phospholipids and thing. They have four connecting rings of carbon and hydrogen. They do not provide any energy. And cholesterol is the best known sterol, and everybody talks about cholesterol. It is found in every cell in the body, and it is required for a large number of physiological processes. And so you find that cholesterol is essential. But if you have high cholesterol level, this can lead to cardiovascular diseases. The counterpart of cholesterol, which is found only in animal kingdom, is the plant sterols or the phytosterols, which are found in plants. So that is why when you see the advertisement, all of you should remember, when you see most of the advertisement for oil saying zero cholesterol, you should know that is a wrong advertisement because no plant oil can contain cholesterol. Cholesterol can be present only in ghee, butter, and other animal fats. No plant oil can contain cholesterol. So if you look at the cholesterol structure, it has this backbone of three six-membered rings, one five-membered ring with a hydrophobic chain attached. This is a precursor of vitamin D. It is the precursor to bile acids, and it is also the precursor to the sex hormones, testosterone and estradiol. And next, coming to the plant sterols, these are naturally occurring thing. The major plant sterols are beta cytosterol, campestrol, and the stigma sterol. And these plant sterols now are gaining importance as nutraceuticals because some of the plant sterols have been known to bring down the cholesterol levels in the human. That is because the cholesterol, they compete with the uh, in the intestines with the cholesterol for the cholesterol absorption into the intestinal epithelium. So you have ergosterol, which is the plant sterols. So you have cytosterol, campestrol, and stigmasterol. Then food sources of cholesterol and plant cholesterol comes mainly from animal products, I told you, and phytosterols come from plant products, and they are in plants. One of the plant phytosterols which is allowed in the food industry and which is allowed with a health claim is a stanol, and and you will see the stanol in a butter-like preparation. It is the only product in India so far which is allowed the health claim that eating 3 grams of this will bring down your cholesterol. Because to use a health claim, you have to take permission from FSSAI. And then you have the lipoproteins. So the lipoproteins, you have 3 different types of lipoproteins. You have the very low density lipoprotein, which is made up of triglycerides and cholesterol. You have the low density lipoproteins, which contain or tells you and known as the bad cholesterol. And then you have the high density lipoprotein, and that is known as the good thing. These are the water soluble forms of the lipids, and they are used in transporting lipids throughout the bloodstream. But LDL, VLDL, and HDL are 3 parameters in your blood, will tell you whether you are prone to cardiovascular diseases or not. Then you have the waxes. The waxes are again hydrolyzable lipids, but these are long chain esters of monohydroxy alcohols. So beeswax, you see, is the fatty acid ester of palmitic acid. So you have palmitic acid, that is the 16 carbon, and then you have a very long chain alcohol. Okay, this is a very long chain alcohol, and that is beeswax. So what does wax do? Wax is hydrophobic. Okay, so they will repel water. So in plants, the wax on the leaves or thing will prevent loss of water and damage from press. In humans and animals, it provides waterproof coating on the skin. So if you look at a duck on it, you will see that it has actually outside of it has got wax coated, and you will see that they never appear to be wet. So they can just shrug off all the water from them. So the waxes that are allowed in the food industry, because they are used as coating material for fruits and vegetables to prevent transpiration and to keep them fresh for longer. 3 different waxes are allowed, that is beeswax, which is ceryl myristate, carnauba wax, which is myricil cerotate, and the spermaceti wax, which is cetyl palmitate. So these 3 waxes are allowed in the food industry. Then we look at the eicosanoids. The eicosanoids, you have prostaglandins and leukotrienes. These contain fatty acids which have 20 carbon, and these eicosanoids are all very potent compounds, and they are synthesized in response to an external stimulus. And unlike the hormones, these are local mediators, and they perform their function in the area where they are synthesized. Not like hormones. If you look at hormones, they're synthesized in one part of the human body, but the actual function is in the other part of the human body. Then you have the prostaglandins, as I said, is an eicosanoid. These prostaglandins have a large number of physiological properties, and they are responsible for the inflammation. So you have prostaglandin F and prostaglandin E. And these prostaglandins decrease gastric thing. They are known to inhibit platelet aggregation. They stimulate uterine contractions, and they relax smooth muscles. And the 2 enzymes which are responsible for prostaglandin synthesis are the cyclooxygenases. So you have COX-1 and COX-2. Have you ever wondered when you have a headache, why would you take aspirin or you take ibuprofen and then you are relieved from the headache? That is because this aspirin and ibuprofen can inhibit the enzyme cyclooxygenase uh, and preventing the formation of these inflammatory factors such as prostaglandin 1 and prostaglandin 2. So most of the pain relievers are inhibitors of cyclooxygenase. So now just let's look at some of the applications and things of oils in the food industry. If you look at the oil, refined oil is sold, and FSSAI has got parameters for both the crude oil and the refined oil. If the oils are extracted by the solvent extraction process, that is by using hexane, then before being sold to the market, they must be refined. So what does refining do? Refining, the word itself says, it removes the unwanted parts or unwanted particulate matter. So the refining process, you see, they do watering, which or what is called as degumming, which removes lecithin and the gums. Then they do add alkali to deacidify so that it removes all the free fatty acids which are produced by hydrolysis or so. Then they add soda and watercress to do further degumming. In that, then bleaching, the oils are bleached, and then it is passed, steam is passed to remove some smell called deodorization. So you have different refining processes of oils, and people are concerned that since chemicals are used in the refining process of oils, they are deleterious to health. And so now the fad is to use either crude oils or to use cold pressed oil. So now let's come to the lab, and as food analysts, how do you evaluate the oils? We have a number of parameters to evaluate the oils, and you see these parameters include both the physical as well as the chemical properties. It also includes the organoleptic properties. So the organoleptic properties are the transparency, color, odor, and taste. The physical properties are by measuring the viscosity and the relative density, the refractive index, the smoke point, the flash point, the melting point, and the freezing point. These parameters, the acid value, saponification value, iodine value, peroxide value, all these give you an idea of what is the chemical constituent of the fat, whether it is a saturated fat, how much of saturated fatty acids it contains, and so on. And then you have the degradation also can be evaluated by parameters such as the acid value, the carbonyl value, the peroxide value, and rancidity. So just let's look at viscosity and density. This viscosity depends on the amount of saturation and unsaturation. And uh, uh, apparently you will see mustard oil is, if you look at mustard oil and compare it with corn oil, mustard oil is much more viscous than corn oil. So viscosity and density decrease with an increase in unsaturation. So you see most of the plant oils are less viscous and less dense than the saturated ones, such as the mustard oil. SAP value, saponification value, it is an index of the mass of the fatty acid, and the lower SAP value tells you that you have larger more fatty acids that make up the triglyceride. Iodine value gives you information on the degree of unsaturation of the fat, and you can divide. Higher the iodine value, higher is the degree of unsaturation. So if you take for example, oleic acid, take for example olive oil, you will find that the iodine value of olive oil will be much higher than the iodine value of coconut oil. Acid value measures the content of free fatty acids, and it tells you a measure of the rancidity. So higher the acid value, higher the degree of degradation, whether it is by hydrolysis or by oxidation. Then you have parameters such as flash point, which is defined as the temperature at which an ignition source causes the vapors of the oil to ignite. You can determine the flash point by an apparatus which is called the Penske apparatus. It's a closed cup equilibrium method, and it is temperature is given in degrees Celsius. You have refractive index. So this refractive index tells you about the oil. It tells you about the purity of the oil, because every oil has got a standard refractive index. You can measure the unsaponifiable matter, because this is the matter which cannot be saponified or made into soap. So it tells you all the other matter which is present in the oil, and it also tells you how well the oil has been refined. So if it is a very well refined oil, you will see that the unsapped matter has to be almost negligible. Peroxide value gives you a degree of the degradation of the oil. The higher the peroxide value, the higher the oil has been oxidized. And peroxide value, acid value, all these must actually correlate with each other. You can also determine the oxidation by chemical methods, such as the para-anisidine value and the carbonyl value, which describes the total amount of carbonyl compounds which are secondary oxidation products. So therefore, the tests in oils you can carry out, if you look at all the tests which have been given for fats and oils, you can tell the physical properties, the chemical properties, as well as the degradation of the oil. Now, another important parameter which has been included for the testing of oils is what is known as the total polar compounds, because it has been found that these total polar compounds are carcinogenic, and so therefore FSSAI has included this in the list. So where do these total polar compounds come? When you do deep fat frying, that is, when you fry foods in hot oil, foods contain moisture. So what happens is some of the moisture from the food gets into the oil, and as the oil is heated and the food, which is a complex matter, is added to the oil, you will see that oxidation products will be there, polymerization products of the oil can come in, and hydrolysis products of the oils can come in. So essentially then, as you keep using the oil, you'll have more of oxidation products, more of the polymers, and more of the free fatty acids, and all these contribute to the polar compounds. So the total polar compound TPC content will tell you when the frying oil should be discarded, because the habit is to use oil to fry and then keep frying in that oil till the oil is over. In the industry also, they tend to replenish the oil by just adding fresh oil to the oil every time. But however, continuous frying helps to build up the TPC, and these total polar compounds have a detrimental effect on consumers' health. So by measuring the total polar compound content, you can tell when the oil has to be discarded. Oils can be interestrified, and you must have heard of interestrified fats and oils. So, interesterification of fats and oils is nothing but shuffling the fatty acids in the three different positions of the glycerol moiety. So, we have SN1, SN2, and SN3. So, by moving the fatty acids from position 1 to 2 or to 3, you can change the the constituency of the fat or the oil. And how can you achieve this? You can achieve this by a chemical means, or you can achieve this by enzymatic means. So the chemical way of interesterifying oils is very random. So you do not get exactly what you want. So you get a bunch of interesterified, and it is done by using sodium methoxide. So this tells you in explains to you in a better way of how interesterification occurs. So you take two different fats, maybe one could be an oil or one could be a fat, which the fatty acid composition is entirely different. You mix the two, and in the presence of sodium methoxide, if you allow them to react, what you see is these are the different combinations of the new fats that you will see. And all of these are called as the interesterified components. So you see you have SOS. So it has become S as taken here. You have from down, you have a S over here, and then you have a palmitate in the SN3 position. You can get all the three S, you can get with the oleic acid. So here what happens when you use chemicals, for interesterification, it becomes a random process. However, if you use an enzyme lipase, which is very specific for breaking the ester bond, then you can get targeted interesterified fats. So the same two fats, if you use a lipase, you see you get only these three. So you get the parent, you get the two parent, and you get the interesterified fat. So this can be purified and can be sold as interesterified fat. The advantage of reshuffling, or you would ask, why do we need interesterified fats, is because you want to create specific fats. And one of the products that has been created is a product called beta pol, which is used in infant formula product, and it mimics the positional composition of human breast milk. The human breast milk fat. So this, by interesterification, they have been able to produce a fat which resembles breast milk fat, and now this fat can be added to infant formula products. By interesterification, also you can prepare cocoa butter equivalents. Cocoa butter is very expensive and cannot be used all the time. So in confectionery, by interesterification, cocoa butter equivalents have been produced. Then you have structural lipids, which are similar to interesterified fats. And here, the name itself says it is a structured lipid. Okay, so in these structured lipids, you see the TAGs, they have long chain fatty acids at the SN1 and SN3. And so in a structured lipid, you can replace the long chain fatty acid at the SN1 and the SN3 with medium chain fatty acids such as caprylic acid or capric acid, or you can replace them with the omega-3 fatty acids, that is DHA, EPA, and DPA, or with the omega-6. So that is a structured lipid. So although structured lipids are interesterified fats, they are actually directed. You can make them have the lipids by using a specific lipase you can target the fatty acid to the SN1 position or the SN3 position of a fat. So the reason why medium chain fatty acids are used in the structured lipids are they are more easily hydrolyzed, and they are more medium chain fatty acids are more readily absorbed and metabolized into energy rather than being accumulated in your adipose tissue. So the structural lipids are a concentrated and readily available source of energy and have a reduced tendency to promote obesity. So again, the structural lipids becomes a functional food or a nutraceutical. So the application, just as in the interestrified, is to form a human milk, to make human milk fat substitutes, oil enriched with essential or long chain omega-3 fatty acids, and oil enriched with medium chain fatty acids for specific nutritional or medical applications. And then you can make cocoa butter equivalents, because you see cocoa butter is got from the cocoa bean, and it consists mainly of palmitic acid, stearic acid, and oleic acid, which gives the product its characteristic hardness at room temperature. The price of cocoa butter is very high, and it fluctuates, and it depends on the availability of the bean and the maturity of the bean. So cocoa butter equivalents are made by starting with palm oil, the mid fraction, which has high amounts of P in it, that is the palmitate, oleic acid, and palmitate, and now it's mixed with saturated stearic acid and palmitic acid, and a very specific lipase is being used, and you see now you get the structured lipid, which has got a fatty acid composition similar to cocoa butter, not exactly the same as cocoa butter. Then you have a group of compounds known as fat replacers, because nowadays we are all in the habit of looking for low fat, low carbohydrate food. There are two types of fat replacers known. One is the fat substitutes, and the other is the fat mimetics. These fat substitutes are lipid or fat-based fat replacers, and where they have modified the fat, okay, or modified carbohydrate, or modified protein, but there is a base amount of fat, and they can be used. The properties will be similar to or close to that of a fat or oil, and it will be stable at cooking and frying temperature. On the other hand, a fat mimetic is an imitation fat which contains no fat in it. It has properties which are entirely different from the fat. It actually mimics the fat and fools you to think that you are eating fat, and you have that feel that you are eating the fat, and it cannot replace the fat on a one-to-one basis, whereas a fat substitute can replace it. And this fat mimetic absorbs a substantial amount of water, and so therefore fat mimetics cannot be used for frying, whereas a fat substitute can be used for frying and cooking, because the backbone of it, some of it will be fat. So the fat substitutes, if you look at them, the reason they're called substitutes is that you will have fewer calories. So you can have carbohydrate based fat substitutes, protein based fat substitutes, or a fat based fat substitutes. So majority of the fat substitutes are carbohydrate based, as you will see in this one. This olestra is available. And what is olestra? Olestra is a modification of sucrose. Okay, it is a polyester of sucrose. So this is the sucrose molecule, and this is linked to fatty acids. So R is the fatty acid, and this has 0 kilocals per gram. So its molecular constitution prevents its hydrolysis by gastrointestinal enzymes. You have another carbohydrate based fat substitutes. It is the backbone is sorbitol, where the hydroxyl groups of sorbitol are all esterified with fatty acids, and this is a clear liquid. It can be used for frying and baking, but however, this, unlike cholesterol, which is 0 kilocals per gram, gives you about 1 to 2 kilocals per gram, and it contains oleic acid, linoleic acid, and stearic acid. These are all man-made, the fat substitute and the fat mimetic. So I just want to go back and tell you, you see the fat substitute is base is either a carbohydrate, protein, or a fat, and you should have a fatty acid to give it the properties of a fat. But the fat mimetic need not contain or will not contain any fatty acid. So here are some examples of the carbohydrate based fat substitutes that are available in the market. So here you have carbohydrate based, you have protein based, you have fat based, and you have a combination of the two. And so with this, I have given you an overview of fats and lipids, fatty acids, both in terms of their role in food science and technology, as well as the role of lipids in for physiology or for the human body. Yes, I'm done, Kavita. What is the thing forward?